Here's something that bothered me for weeks after I learned it. You know how we talk about Jupiter being a gas giant? How it's this massive ball of gas with no solid surface, just atmosphere all the way down. That's what I was taught in school. That's what every documentary says. Gas giant, ball of gas. Except that's not quite right. And when you actually dig into what Jupiter is, what it's really made of, what's happening inside it, what it does to space around it, it's so much stranger than big ball of gas suggests. So strange that some of the things I'm going to tell you sound like science fiction, but they're not. They're real, based on actual spacecraft data, actual measurements. Jupiter is not what you think, and I mean that literally. Most of what people believe about Jupiter, even people who are interested in space, is either oversimplified to the point of being wrong, or based on assumptions that turned out to be false when we actually sent probes there. Let me tell you what Jupiter actually is, because it's weirder and more hostile and more fascinating than almost anyone realizes. First, let's deal with the gas giant thing, because this is where the misconception starts. When you hear gas giant, you probably imagine, what? A big ball of gas. Like a balloon, maybe, just enormous. Atmosphere all the way through, no surface to land on because it's just gas. That mental image is wrong. Not completely wrong, but wrong enough that it misses what makes Jupiter genuinely strange. Yes, Jupiter is mostly hydrogen and helium, about 90% hydrogen, 10% helium, with trace amounts of other elements. Same basic composition as the Sun, actually. And yes, the outer layers are gaseous, but as you go deeper into Jupiter, something happens that doesn't happen on Earth, that doesn't happen with any gas you've ever encountered in everyday life. The pressure increases, obviously, more mass above you pressing down. But Jupiter is so massive, 318 times Earth's mass, that the pressure gets extreme very quickly. And under extreme pressure, hydrogen stops behaving like a gas. At around 1 million atmospheres of pressure, roughly 1,000 kilometers down into Jupiter, hydrogen becomes liquid. Not because it's cold. Jupiter's interior is hot, but because the pressure is so immense that it forces the hydrogen molecules close enough together that they behave like a liquid. Liquid metallic hydrogen, actually, which is a state of matter that doesn't exist naturally anywhere on Earth. We can barely create it in laboratories for microseconds. Go deeper. The pressure keeps increasing. Around 2 million atmospheres, deeper still, the hydrogen becomes something even stranger. The pressure is so extreme that electrons are stripped from hydrogen atoms entirely. You get a soup of free electrons and protons. This is metallic hydrogen, called that because it conducts electricity like a metal, even though it's made of hydrogen. It's not a gas. It's not really a liquid in any normal sense. It's something else. A state of matter that only exists in the interiors of gas giants. So Jupiter doesn't have a surface the way Earth does, a clear boundary between atmosphere and solid ground. But it's not just gas all the way down either. It's layers. Gas transitioning to liquid transitioning to metallic hydrogen transitioning to, well, we're not entirely sure what's at the very centre. Probably a rocky core, maybe 10 to 20 times Earth's mass, but we can't see it, and we've never directly measured it. This is what I mean. When I say Jupiter is not what you think, it's not a big ball of gas. It's a layered structure of hydrogen in increasingly exotic states, surrounding a core we can't observe, generating a magnetic field that extends millions of kilometers into space, all of it rotating so fast that the whole planet bulges at the equator. And all of this entire planetary structure, is held together by its own gravity. Jupiter is so massive that it compresses itself into these extreme states. It's a failed star, in a sense. If it had been about 75 times more massive, it would have ignited fusion in its core and become a star instead of a planet. As it is, it's not quite massive enough, but it's close. Jupiter generates more heat than it receives from the Sun. The planet is actually shrinking very slowly, compressing under its own gravity, and that compression generates heat. Jupiter radiates about 1.6 times as much energy as it absorbs from sunlight. Let that sink in. Jupiter is not a cold, dead ball of gas. It's an active, dynamic object that produces its own heat through gravitational compression. It's glowing in infrared, not visible light. It's not a star, but it's putting out heat. A lot of heat. Now let's talk about the second major misconception. You've probably heard this one. Jupiter protects Earth. It's like our guardian, our big brother, using its massive gravity to sweep up asteroids and comets that would otherwise hit Earth. There are popularizations of astronomy that present this as fact. Jupiter the protector, Jupiter the shield. This is complicated and probably wrong, or at least not as simple as it's usually presented. Yes, Jupiter's gravity affects the orbits of asteroids and comets. Obviously, it's the most massive planet in the solar system by far. Its gravity dominates the outer solar system. There's even a family of asteroids called the Trojans that orbit in Jupiter's Lagrange points, gravitationally stable positions ahead of and behind Jupiter in its orbit. Jupiter's influence is huge, but does it protect Earth? Does it reduce the impact rate on our planet? Some computer simulations suggest it does. Some suggest it doesn't. Some suggest Jupiter actually increases the number of impacts on Earth by perturbing objects in the outer solar system and sending them sunward. The truth is, we don't know for certain. The dynamics are complicated. The solar system is a chaotic gravitational environment, and running accurate simulations over billions of years is difficult. What we do know is that Jupiter's gravity has shaped the asteroid belt between Mars and Jupiter. There are gaps in the belt, Kirkwood gaps, where Jupiter's orbital resonances have cleared out asteroids. Objects in those gaps get perturbed by Jupiter over time and eventually end up somewhere else. Some of those somewhere elses are in the inner solar system. Some are ejected entirely. So Jupiter does clear out certain orbital regions, but whether that makes Earth safer or more dangerous is genuinely unclear. The idea of Jupiter as Earth's protector is probably oversimplified. It's one of those things that sounds good, that makes for a nice narrative. Big Jupiter protecting little Earth, but the reality is messier. What we know for sure is that Jupiter is dangerous. Not to Earth necessarily, but to spacecraft. To anything that gets close to it. Because Jupiter doesn't just have gravity, it has a magnetosphere. And that magnetosphere is a radiation hell. Here's something most people don't know. Jupiter has the strongest magnetic field of any planet in the solar system, stronger than Earth's by a factor of about 20,000 times stronger. This is because of that metallic hydrogen I mentioned earlier. It's electrically conductive and it's moving. Jupiter rotates once every 10 hours, which is absurdly fast for something that massive. That rotation creates a dynamo effect, generating an enormous magnetic field. That magnetic field traps charged particles, electrons and ions, from the solar wind and from Jupiter's volcanic moon Io. These particles spiral along the magnetic field lines, creating radiation belts around Jupiter, similar to Earth's Van Allen belts, except Jupiter's radiation belts are vastly more intense. How intense? If you were in a spacecraft near Jupiter, say at the orbit of the moon Io, you'd be receiving a radiation dose of about 36,000 rem per day. That's enough to kill you in hours. For comparison, a lethal dose for humans is about 500 rem total. You'd get that in 20 minutes at Io's orbit. This is why the Galileo spacecraft, which orbited Jupiter from 1995 to 2003, had to be carefully shielded, and its orbit had to avoid the most intense radiation regions. Even so, the radiation degraded its electronics over time. By the end of the mission, multiple systems were failing. The spacecraft was dying from radiation exposure. This is also why exploring Jupiter's moons is so challenging. Europa, which is one of the most interesting targets in the solar system for the search for life, sits right in the middle of Jupiter's radiation belts. Any spacecraft that orbits Europa has to contend with radiation levels that will destroy electronics in relatively short time. It's a genuine engineering challenge. The Juno mission, which has been orbiting Jupiter since 2016, deals with this by using a highly elliptical orbit. It swings in close to Jupiter, takes measurements, then swings back out to a safe distance. It spends most of its time in the less intense radiation regions and only dips into the really bad areas for a few hours per orbit. And even so, it's heavily shielded. The electronics are inside a titanium vault, and it's still accumulating radiation damage. The mission has been extended multiple times, but eventually, the radiation will kill it. This is Jupiter. Not a gentle giant. Not a protective big brother. A radiation environment so harsh it destroys spacecraft. Now let's talk about what you can actually see when you look at Jupiter. Those bands. Those stripes. The great red spot. We've all seen images. They're beautiful. They make Jupiter instantly recognizable. But what are you actually looking at? Most people think they're looking at the surface. They're not. There's no surface. You're looking at the tops of clouds. Ammonia ice clouds, mostly, at an altitude where the pressure is maybe 0.5 to 1 atmospheres. Basically Earth sea level pressure. Below that, deeper in the atmosphere, there are other cloud layers. Water ice, ammonium hydrosulfide, but you can't see them because the upper ammonia clouds are opaque. Those bands, the light zones and dark belts, are wind patterns. Jupiter's atmosphere is divided into east-west jet streams, similar to Earth's jet streams but on steroids. Wind speeds in some of Jupiter's jets exceed 600 kilometers per hour. That's Category 5 hurricane speed sustained constantly, forever across the entire planet. The light zones are rising gas, updrafts bringing material from deeper in the atmosphere. As the gas rises and cools, ammonia condenses out and forms those white clouds. The dark belts are descending gas, downdrafts where the ammonia has already condensed and fallen deeper, leaving darker compounds visible. Basically, Jupiter's atmosphere is organizing itself into giant convection cells, driven by the heat rising from the interior. And here's something that surprised me when I learned it. We don't fully understand why Jupiter has this banded structure. We know it's related to rotation and convection and the Coriolis effect. We can model it, but Earth doesn't look like this. Neither does Saturn, exactly. Jupiter has a specific pattern, bands at specific latitudes, jets at specific speeds, and we're still working out exactly why. What we've learned from recent missions is that these bands aren't just surface features. The jets extend deep into the atmosphere. The Juno spacecraft has been measuring Jupiter's gravity field in exquisite detail, and those measurements show that the jet streams extend down maybe 3,000 kilometers into the planet. Below that depth, the pressure is so high that friction becomes significant and the jets dissipate. But that's deep. That's a significant fraction of Jupiter's radius. These aren't just surface winds. They're massive atmospheric structures extending into the planet. Then there's the Great Red Spot. Everybody knows the Great Red Spot. It's Jupiter's most famous feature, a giant storm bigger than Earth that's been raging for at least 150 years, possibly 400 years depending on whether historical observations were seeing the same feature. But here's what most people don't realize. The Great Red Spot is shrinking. It's been getting smaller since at least the late 1800s when we started getting good telescopic observations. Back then it was maybe 40,000 kilometers across, 3 times Earth's diameter. Now it's about 16,000 kilometers across. Still bigger than Earth, but smaller than it used to be, and the rate of shrinkage might be accelerating. We don't know why. We don't know if it'll disappear entirely or stabilize at some smaller size. We don't even know exactly why it's red. The color is probably due to complex organic compounds formed by ultraviolet radiation acting on simpler chemicals in the atmosphere, but we don't know which compounds. We don't know why the spot is red, but the surrounding clouds aren't. It's one of those things where we have a general idea, but not a complete understanding. What we do know is that the Great Red Spot is an anticyclone, a high-pressure system rotating counterclockwise in Jupiter's southern hemisphere. It's essentially a permanent hurricane, though that's not quite the right analogy, because hurricanes on Earth derive energy from warm ocean water, and Jupiter doesn't have oceans. The spot's energy comes from Jupiter's internal heat and from absorbing smaller storms. We've watched it eat smaller storms. They get too close, get caught in the spot's circulation, and merge with it. Why doesn't it dissipate like storms on Earth do? On Earth, hurricanes die when they hit land or move over cold water because they lose their energy source. But Jupiter has no land, no surface, just atmosphere all the way down, and the planet is generating heat from its interior. So storms on Jupiter can potentially last indefinitely as long as they maintain their structure. But the Great Red Spot is shrinking anyway. Something is causing it to lose energy or change form. We don't know what. It's possible the shrinkage is temporary and the spot will grow again. It's possible it'll vanish in the next few decades and Jupiter will look noticeably different. We're watching a planetary scale atmospheric feature evolve in real time, and we don't fully understand the process. Now I want to talk about something that doesn't get enough attention: Jupiter's moons. Not just the 4 big ones, Io, Europa, Ganymede, Callisto, though those are remarkable enough. I mean all of them. Jupiter has at least 95 known moons. 95. And there are probably more waiting to be discovered. Most of them are tiny. Irregular chunks of rock and ice a few kilometers across. Captured asteroids, basically. Jupiter's gravity is strong enough that it can capture passing objects and pull them into orbit. These small outer moons have weird, eccentric orbits. Some of them orbit backwards, retrograde motion. They're gravitational debris, but the 4 big ones, the Galilean moons, discovered by Galileo in 1610, are worlds in their own right. Each one is bigger than Pluto. Ganymede is bigger than Mercury. These aren't moons in the sense of being minor objects. They're planetary mass bodies that happen to orbit Jupiter instead of the Sun, and each one is strange in its own way. Let me tell you about Io first, because Io is genuinely one of the weirdest objects in the solar system. Io is the most volcanically active body we've ever discovered, anywhere. Earth has maybe a few dozen active volcanoes at any given time. Io has hundreds. Its surface is constantly being resurfaced by volcanic activity. There are no impact craters on Io. Any crater that forms gets buried by lava within a few million years. The entire surface is young, geologically speaking. Why? Tidal heating. Io orbits very close to Jupiter, about 420,000 kilometers, similar to the Moon's distance from Earth, but Jupiter has far more mass than Earth, so its tidal forces are enormous. As Io orbits, Jupiter's gravity squeezes and flexes it, literally kneading the Moon like dough. This flexing generates friction in Io's interior, which generates heat, which melts rock, which creates volcanism. And it's not gentle volcanism. Io's volcanoes are violent. Plumes of sulfur and sulfur dioxide erupt to altitudes of hundreds of kilometers. We've measured eruption velocities of 1 kilometer per second. That's fast enough to reach escape velocity on Io. Some of the erupted material doesn't fall back down, it escapes into space. Where does it go? It forms a torus, a donut-shaped cloud of ionized sulfur and oxygen, around Jupiter at Io's orbital distance. This material gets caught in Jupiter's magnetic field, gets accelerated to high speeds, and slams into the other moons. Europa, Ganymede. They're getting bombarded by high-energy ions from Io's volcanoes. It's wild. The surface of Io is yellow and orange and white and black. Sulfur compounds in different states, frozen sulfur dioxide, volcanic rock. It looks like a mouldy pizza, honestly. Not beautiful in a conventional sense, but striking. Alien. Then there's Europa, and Europa is where things get really interesting from an astrobiology perspective. Europa is an ice moon. Its surface is a shell of water ice, very smooth, very young, maybe only 40 to 90 million years old based on crater counts. That's recent in geological terms. The surface is being renewed somehow. There are very few craters. Instead, there are cracks and ridges and chaotic terrain where the ice has fractured and refrozen. And beneath that ice, we're very confident about this based on gravitational measurements and magnetic field observations. There's a global ocean, liquid water, a subsurface ocean that probably contains more water than all of Earth's oceans combined. The ice shell is maybe 10 to 30 kilometers thick. Below that, ocean, maybe 100 kilometers deep. Below that, a rocky seafloor. This ocean is kept liquid by tidal heating. Same mechanism as Io, but less intense because Europa is farther from Jupiter. The tides flex Europa's interior, generate heat, keep the ocean from freezing solid. And this ocean might be habitable. Not habitable for humans. It's dark, it's cold, it's under enormous pressure, but habitable for microbial life, potentially. On Earth, we have ecosystems in the deep ocean that survive without sunlight, deriving energy from hydrothermal vents and chemical reactions. Europa might have similar vents on its seafloor. Heat from the rocky core, minerals dissolved in the water, chemical energy available. It's plausible that life could exist there. We don't know if it does. We have no direct evidence, but Europa is one of the most promising places in the solar system to search for extraterrestrial life, which is why there are multiple missions planned to Europa in the coming decades. NASA's Europa Clipper is launching in 2024, arriving at Jupiter in 2030. ESA's JUICE mission launched in 2023. Both will study Europa closely, looking for evidence of the ocean, analysing the surface composition, searching for plumes of water erupting from the surface. If Europa has plumes, and we've seen hints of them in Hubble observations, though they're not confirmed, then we might be able to fly through them and sample the ocean water directly without even landing. Just fly through a plume, collect particles, analyse them. If there's life in that ocean and it's getting ejected into space through cracks in the ice, we might find it. This is why Europa matters. It's not just a moon of Jupiter, it's potentially one of the most important targets in the search for life beyond Earth. Ganymede is the largest moon in the solar system, bigger than Mercury. It's the only moon that has its own magnetic field, generated by a liquid iron core, similar to Earth. It also probably has a subsurface ocean, though deeper beneath the ice than Europa's. Layers of ice and water actually, high pressure ice at the bottom, liquid water in the middle, regular ice on top. Weird structure. Callisto is the most heavily cratered object we've seen in the solar system. Its surface is ancient, maybe 4 billion years old. It's been sitting out there getting hit by asteroids and comets for the entire history of the solar system, and the surface has barely changed. Dead world. But it might also have a subsurface ocean. Magnetic field measurements suggest liquid water somewhere deep inside. So Jupiter doesn't just have moons, it has a mini solar system, 4 planetary mass bodies, each completely different from the others. Active volcanism on 1, subsurface oceans on at least 2, possibly 3, ancient cratered surfaces on 1, all of them in orbit around this giant radiation-blasted planet. And here's something that struck me when I really thought about it. These moons are close to Jupiter. Really close. Io is only 6 Jupiter radii from the planet's centre. That's 421,000 kilometres. From Io's surface, Jupiter fills 20 degrees of sky. Imagine looking up and seeing Jupiter, that massive striped ball, taking up a huge chunk of the sky, phases visible as Io orbits, the great red spot drifting across the face of the planet. It would be spectacular and terrifying, because you'd also be sitting in a radiation environment that would kill you, and if you were on Io, you'd be on a world with hundreds of active volcanoes and a surface that's constantly being reshaped by lava flows. Not a safe place, but the view would be incredible. Now let me tell you about something most people don't even know exists. Jupiter has rings. Not big spectacular rings like Saturn, but rings nonetheless. Thin, faint, made mostly of dust. And we didn't discover them until 1979 when Voyager 1 flew past. Why didn't we see them earlier? Because they're incredibly faint, dark. They don't reflect much light. From Earth, even with good telescopes, they're basically invisible. You need to be close to Jupiter, looking back toward the sun with the planet blocking the direct sunlight, to see them clearly, which is exactly what Voyager 1 did. Took a long exposure while positioned on Jupiter's night side, and there they were. Where do these rings come from? Not the same way Saturn's rings formed. Saturn's rings are probably the remains of a shattered moon or a comet that got too close and was torn apart by tidal forces. Jupiter's rings are constantly being replenished by dust kicked up from small inner moons by meteorite impacts. These moons, Metis, Adrastea, Amalthea, Thebe, are tiny, only tens of kilometers across. When a meteorite hits them, debris gets ejected into orbit around Jupiter. That debris becomes the rings. The rings are temporary on geological timescales. The dust particles slowly spiral into Jupiter due to electromagnetic drag and atmospheric friction, but they're constantly being replenished by new impacts, so the rings have existed for probably millions of years and will continue existing as long as those small moons are there to supply material. Why does this matter? Because it tells us something about the environment near Jupiter. The inner solar system is full of small debris, meteorites, micrometeorites, dust. This stuff is constantly hitting moons and planets. We see the effects on Earth, meteorites, shooting stars. On Jupiter's small inner moons, which have no atmosphere to protect them, the bombardment is constant and severe enough to generate visible ring systems. It's a reminder that space isn't empty. It's full of debris moving at high speeds, and anything out there is getting hit constantly. Now let's talk about Jupiter's magnetosphere in more detail, because this is where things get genuinely weird. I mentioned earlier that Jupiter's magnetic field is about 20,000 times stronger than Earth's, but that number doesn't really convey what it means. Earth's magnetosphere, the region of space dominated by Earth's magnetic field, extends about 10 Earth radii on the sunward side and trails out behind Earth in a long magneto-tail. It's big enough to protect us from the solar wind and cosmic rays. It creates the auroras when charged particles hit the upper atmosphere. Jupiter's magnetosphere is enormous. It extends about 50 to 100 Jupiter radii on the sunward side depending on solar wind pressure. That's roughly 7 million kilometers. 7 million? If it were visible to the naked eye from Earth, it would appear larger than the full moon in our sky, even though Jupiter is hundreds of millions of kilometers away. On the night side, the side facing away from the sun, Jupiter's magnetotail extends even farther. Past Saturn's orbit, we're talking hundreds of millions of kilometers, possibly past the orbit of Saturn. When Cassini was on its way to Saturn, it detected bursts of energetic particles that probably originated from Jupiter's magnetotail, even though Saturn was the target and Jupiter was far away. This is not a gentle magnetic field, it's a monster, and it does things that Earth's magnetosphere doesn't do. For one, Jupiter produces intense radio emissions, not just radio noise, structured, powerful radio bursts that we can detect from Earth with relatively simple equipment. Amateur radio operators have been picking up Jupiter's radio emissions since the 1950s. It sounds like static, like bursts of noise, but it's coming from Jupiter, from interactions between the magnetic field and charged particles, particularly from Io's plasma torus. The mechanism is complicated but basically goes like this. Io's volcanoes eject sulfur and oxygen into space. This material gets ionized by solar ultraviolet radiation and by impact with energetic particles. The ionized material, plasma, gets caught in Jupiter's magnetic field and forms a torus around the planet at Io's orbital distance. This plasma is forced to rotate with Jupiter's magnetic field, which is rotating once every 10 hours, but Io itself orbits slower, once every 42 hours, so there's a speed mismatch. This mismatch creates electric currents, millions of amperes flowing between Io and Jupiter along magnetic field lines. These currents accelerate electrons to high speeds. Those electrons spiral along the magnetic field, and when they reach Jupiter's poles, they slam into the upper atmosphere and create auroras. But they also generate radio emissions through a process called cyclotron radiation. The result is radio bursts that we can detect from Earth. Jupiter is the second brightest radio source in the sky after the Sun. Not in visible light, Jupiter's too far away and too faint to compete with stars in visible wavelengths, but in radio wavelengths it's extremely bright. This was a surprise when it was first discovered in the 1950s. Nobody expected a planet to be a strong radio source. Stars, yes. The sun produces radio emissions, but a planet, that was unexpected. And it told us something important. Jupiter has a powerful magnetic field and complex interactions between that field and its moons. We've since learned that the radio emissions vary. They're stronger when Io is at certain positions in its orbit. They're affected by the solar wind. They're structured in ways that we're still working to fully understand. Studying Jupiter's radio emissions is an active area of research. Now let me tell you about the spacecraft that have visited Jupiter, because each mission has revealed something new and unexpected. Pioneer 10 and 11 flew past in 1973 and 1974. These were the first spacecraft to reach the outer solar system. Before them, we'd only visited the inner planets. Nobody knew if a spacecraft could even survive the journey through the asteroid belt. There were genuine concerns about impacts with debris, but both pioneers made it through safely and flew past Jupiter, taking the first close-up images and measurements. What they found: Jupiter's magnetic field was far stronger than expected. The radiation environment was far more intense than predicted. Pioneer 10's instruments were damaged by the radiation. Some failed entirely. The spacecraft survived, but just barely. This told mission planners that future spacecraft would need heavy radiation shielding. They also found that Jupiter radiates more heat than it receives from the Sun, confirming the internal heat source hypothesis. And they got the first detailed images of the cloud patterns and the Great Red Spot. Voyager 1 and 2 followed in 1979, much more sophisticated spacecraft with better cameras and instruments. They discovered the rings. They discovered active volcanism on Io, the first time we'd seen active volcanism anywhere besides Earth. They took stunning images of all 4 Galilean moons, showing details we'd never seen before. They measured the magnetic field and radiation belts in detail. Voyager also revealed that Jupiter's atmosphere is far more dynamic than anyone thought. They saw storms forming and dissipating. They saw small white ovals, smaller storms similar to the Great Red Spot but temporary. They saw interactions between different jet streams. The atmosphere was turbulent, chaotic, beautiful. Then came Galileo in 1995, not a flyby mission, an orbiter that stayed at Jupiter for nearly 8 years. Galileo revolutionized our understanding of the system. It orbited Jupiter multiple times, each orbit designed to fly past one of the moons for close-up observations. It watched Comet Shoemaker-Levy 9 impact Jupiter in 1994, the first time we'd seen an impact on another planet in real time. The comet broke into pieces and hit Jupiter over several days, leaving dark scars in the atmosphere that persisted for months. Galileo also dropped a probe into Jupiter's atmosphere. The Galileo probe, a heavily armoured capsule designed to survive the entry and descent long enough to take measurements. It entered Jupiter's atmosphere on December 7, 1995, descended under parachute, and transmitted data for about 58 minutes before being crushed by the pressure. What it found was surprising. The atmosphere was drier than expected, less water than models predicted. The winds were stronger than expected, increasing in speed as the probe descended rather than decreasing. And the atmosphere was layered in unexpected ways, regions of different composition and temperature that the models hadn't fully predicted. The probe descended to a depth where the pressure reached about 23 atmospheres and the temperature reached 153 degrees Celsius. Then it stopped transmitting, crushed and cooked by Jupiter's atmosphere. But in those 58 minutes, it sent back the only direct measurements we have of Jupiter's deep atmosphere. Galileo's orbiter continued operating until 2003, when it was deliberately crashed into Jupiter to prevent any possibility of it contaminating Europa with Earth bacteria. By then, radiation damage had degraded many systems. The spacecraft was dying, but it had accomplished far more than its original mission goals. Then came Juno in 2016, and Juno is teaching us things we never expected. Juno's orbit is different from Galileo's. It's a polar orbit, passing over Jupiter's north and south poles, rather than orbiting around the equator, and it's highly elliptical, swooping in close and then swinging back out. This allows Juno to study the polar regions, which previous missions largely ignored, while minimizing radiation exposure. What Juno has found: Jupiter's poles look nothing like the equatorial regions. At the equator, you have those organized bands and zones, east-west jet streams, structured atmospheric flow. At the poles, you have chaos, giant cyclones, each one the size of a large country or small continent, arranged in geometric patterns. At the North Pole, there's one cyclone at the exact pole surrounded by 8 others in an octagonal pattern. At the South Pole, one central cyclone surrounded by 5 others in a pentagonal pattern. Why this pattern? We don't know. We've never seen anything like it anywhere else. These cyclones have been stable for years. Juno has been watching them since 2016, and the patterns remain. They're not temporary features, they're long-lived structures locked in some kind of dynamical equilibrium. Juno has also mapped Jupiter's gravity field with unprecedented precision, and that data reveals that the jet streams extend deep into the planet, about 3,000 kilometers down, before dissipating. We didn't know that before. We thought the jets might be shallow surface features. They're not. They're massive, deep atmospheric flows. And Juno has detected lightning, lots of lightning, more than 400 lightning strikes detected in the first 8 months, and most of it is at high latitudes, near the poles, which is opposite to what happens on Earth, where lightning is most common near the equator. We don't know why Jupiter's lightning is concentrated at the poles. There's also been strange observations of sprites and elves, transient luminous phenomena in the upper atmosphere, similar to what we see on Earth but at much larger scales. These are brief flashes of light associated with lightning, but occurring at high altitude. On Earth they're rare and difficult to observe. On Jupiter, Juno has seen them multiple times. They might be common. Each mission teaches us that Jupiter is more complex than we thought, more dynamic, more varied. The simple picture of a banded gas giant doesn't capture the reality. Jupiter is an active, evolving world with atmospheric phenomena we're still trying to understand. Now let's talk about Jupiter's influence on the rest of the solar system, because Jupiter is not isolated. It's so massive that it affects everything around it. Jupiter contains about 70% of the planetary mass in the solar system. All the other planets combined, Mercury, Venus, Earth, Mars, Saturn, Uranus, Neptune, add up to less mass than Jupiter alone. This gives it enormous gravitational influence. The asteroid belt between Mars and Jupiter exists in the configuration it does largely because of Jupiter. Jupiter's gravity prevented the material in that region from coalescing into a planet. Instead, we have thousands of small bodies, asteroids, in a complex dance of orbits influenced by Jupiter's gravitational pull. Those Kirkwood gaps I mentioned earlier, regions in the asteroid belt where asteroids are rare or absent, are caused by orbital resonances with Jupiter. If an asteroid's orbital period is a simple ratio of Jupiter's orbital period, say 3:1 or 2:1, then it encounters Jupiter at the same point in its orbit repeatedly. Over time, these repeated encounters perturb the asteroid's orbit until it's no longer in the resonant zone. The gaps are cleared out. Some of those perturbed asteroids end up in planet-crossing orbits. They might hit Mars, or Earth, or Venus. So Jupiter's gravity is actively reshuffling the asteroid belt, sending objects into the inner solar system. Whether this increases or decreases Earth's impact rate is, as I said earlier, unclear, but Jupiter is definitely influencing it. Jupiter also affects comets. Long-period comets, the ones coming from the Oort cloud on highly elliptical orbits, sometimes pass close to Jupiter. When they do, Jupiter's gravity can capture them into shorter period orbits, or it can fling them out of the solar system entirely. Jupiter is essentially the gatekeeper for comets entering the inner solar system. The Shoemaker-Levy 9 impact I mentioned earlier was a perfect example of Jupiter's influence. That comet had been captured by Jupiter's gravity decades earlier. It was in orbit around Jupiter, not the Sun, but its orbit was unstable. In 1992, it passed too close to Jupiter, and tidal forces tore it apart into fragments. Those fragments continued orbiting Jupiter for another orbit or two before finally impacting in 1994. We watched the whole thing happen. Telescopes on Earth and the Hubble Space Telescope observed the impacts in real time. Each fragment hit Jupiter like a bomb, creating enormous fireballs that rose above the cloud tops. The impacts left dark scars, debris from the explosions that persisted for months. It was spectacular and violent, and a reminder that impacts still happen in the solar system, even now. Jupiter also might have affected the formation of the solar system itself. There's a hypothesis called the Grand Tack that suggests Jupiter formed farther from the Sun, then migrated inward toward where Mars is now, then reversed course and migrated back outward to its current position. This migration would have stirred up the early solar system, scattering planetesimals, preventing a planet from forming in the asteroid belt region, possibly limiting the growth of Mars. It's not proven, it's a model based on computer simulations trying to explain certain features of the solar system. But if it's correct, then Jupiter's migration history shaped the entire inner solar system. Earth might not exist, or might exist in a very different form if Jupiter hadn't migrated the way it did. So Jupiter is not passive, it's not just sitting out there being big, it's actively influencing orbits, clearing regions, capturing objects, sending comets sunward or flinging them into interstellar space. It's a major actor in the ongoing dynamics of the solar system. Here's something that doesn't get talked about enough. Jupiter is teaching us how to understand planets around other stars, exoplanets. Because for decades we only had our solar system as a reference. We assumed other planetary systems would look like ours. Small rocky planets close to the star, gas giants far out, nice and orderly. Then we started finding exoplanets in the 1990s, and they were nothing like our solar system. The first exoplanets we discovered were hot Jupiters, gas giants orbiting extremely close to their stars, closer than Mercury is to our Sun, massive planets with orbital periods of just a few days, roasting in their star's heat. This made no sense based on our understanding of planetary formation. Gas giants can't form that close to a star. It's too hot. The stellar radiation would blow away the gas before a planet could accumulate it. Gas giants have to form farther out where it's cold enough for ice to condense and create solid cores that can then gravitationally capture gas. So how did these hot Jupiters get there? They must have migrated, formed farther out in their planetary systems, then spiraled inward through interactions with the protoplanetary disk or with other planets. They ended up in close orbits where they definitely didn't form, and this told us something important about Jupiter. Jupiter probably migrated too. Maybe not as dramatically as hot Jupiters. Jupiter ended up at 5 AU from the Sun, not 0.05 AU like some hot Jupiters, but it probably didn't form exactly where it is now. The Grand Tack hypothesis I mentioned earlier is one attempt to explain Jupiter's migration and its effects on the solar system. But here's the key thing. By studying Jupiter up close, measuring its composition, its internal structure, its atmospheric dynamics, we're learning what gas giants are actually like, what they're made of, how they work, and that knowledge applies to exoplanets. When we detect an exoplanet and measure its mass and radius, we can compare it to Jupiter. Similar density, probably similar composition, mostly hydrogen and helium. Higher density, probably has a larger rocky core. Lower density, maybe more helium-rich or puffed up by stellar heating. When we model exoplanet atmospheres, we use Jupiter as a test case. Our models have to reproduce Jupiter's observed properties, the cloud layers, the wind speeds, the temperature structure. If they can't match Jupiter, which we can study in detail, then they probably won't accurately predict conditions on exoplanets we can barely observe. Jupiter is our Rosetta Stone for understanding gas giants throughout the galaxy, and there are a lot of gas giants out there. Maybe 20–30% of Sun-like stars have giant planets. That's billions of gas giants in our galaxy alone. Understanding Jupiter helps us understand all of them. And here's something I find fascinating. We're now finding exoplanet systems that look more like our solar system, giant planets farther out, smaller planets closer in, systems that might have had migration but didn't go as extreme as hot Jupiter's. These systems give us context for our own solar system. They show us that Jupiter's configuration, massive gas giant at 5 AU, is not unique. It's one common outcome of planetary formation, but they also show variation. Some systems have multiple gas giants. Some have gas giants much more massive than Jupiter. Some have configurations we don't fully understand. The diversity is enormous, and every new discovery teaches us something about the range of possible outcomes when planets form around stars. Jupiter is one data point, but it's the best studied data point we have. Every measurement we make of Jupiter, every new discovery from missions like Juno, contributes to our understanding of planets in general. Now let me talk about what we still don't know, because despite all the missions, all the measurements, all the data we've collected, there are fundamental questions about Jupiter we can't answer yet. We don't know exactly what's in Jupiter's core. Is there a solid core at the centre? If so, how massive is it? 10 Earth masses? 20? Is it pure rock, or is it a mixture of rock and ice? Or has the core dissolved into the surrounding metallic hydrogen under the extreme pressure and temperature? Some models suggest the core might be fuzzy, not a distinct boundary, but a gradual transition from enhanced heavy element concentration to pure metallic hydrogen. We can't observe the core directly. We can only infer its properties from measurements of Jupiter's gravity field and modelling. Juno's gravity measurements are the best we have, but they still leave room for different interpretations. The core mass could be anywhere from 0 to 20 Earth masses and still be consistent with the data. We don't know exactly how much water is in Jupiter's atmosphere. Water is important because it tells us where and how Jupiter formed. If Jupiter formed in its current location, it should have a certain amount of water based on the ice content of the solar nebula at that distance. If it formed farther out and migrated inward, it might have more water. If it formed closer in, it might have less. The Galileo probe measured water, but it descended in an unusually dry region, possibly a giant downdraft where water had been depleted. So we got a measurement, but we don't know if it's representative of Jupiter as a whole. Juno has microwave instruments that can peer deeper into the atmosphere and measure water content remotely, but the measurements are still being analysed and there's uncertainty. We don't fully understand Jupiter's internal heat source. Yes, it's shrinking and generating heat through gravitational compression, but the details are unclear. How fast is it shrinking? Is the heat generation rate constant, or does it vary? Are there other heat sources besides contraction? Maybe helium rain deep in the interior as helium separates from hydrogen and sinks toward the core, releasing gravitational energy. Models suggest helium rain might be happening. At certain pressures and temperatures deep in Jupiter, helium becomes immiscible with hydrogen, like oil and water separating. The helium droplets sink, releasing heat. This could explain some of the observed heat output, but we can't confirm it. We can't see into Jupiter's interior. We don't know why the Great Red Spot is shrinking or whether it'll disappear. We don't know why the polar cyclones organise into those specific geometric patterns. We don't know why lightning is concentrated at high latitudes. We don't know exactly how deep the atmosphere extends before it transitions to the liquid interior. There's a lot we don't know. And that's exciting, actually, because it means there's more to discover. More missions to fly, more measurements to make, more surprises waiting. Speaking of future missions, there are several planned or proposed for the Jupiter system in the coming decades. Europa Clipper launches in 2024, arrives at Jupiter in 2030. It'll make dozens of close flybys of Europa, studying the ice shell, looking for the subsurface ocean, analysing the surface composition, searching for plumes. It's not a lander, it's an orbiter that repeatedly flies past Europa, but it'll give us the most detailed look at Europa we've ever had. JUICE, Jupiter Icy Moons Explorer, launched by ESA in 2023, arrives at Jupiter in 2031. It'll study Ganymede, Callisto, and Europa, eventually going into orbit around Ganymede. It's focused on the icy moons and their potential subsurface oceans. There have been proposals for Europa landers, for Io orbiters, for atmospheric probes that would descend deeper into Jupiter than Galileo did, for missions to study Jupiter's magnetosphere in detail. Some of these will probably fly eventually, some won't get funded, but the point is there's ongoing interest in exploring Jupiter and its moons, and there should be, because Jupiter is not fully understood. Every mission reveals surprises. Every new dataset raises new questions. Let me tell you why I think Jupiter matters beyond just scientific curiosity. Beyond the cool images and the interesting moons and the extreme conditions, Jupiter represents a different path, a different outcome for how a planet can form and evolve. Earth is one kind of planet, rocky, with an atmosphere, with liquid water on the surface, with life. We understand Earth reasonably well because we live here. We can study it in detail. But Jupiter shows us that planets can be radically different. No surface, mostly hydrogen and helium. Magnetic fields strong enough to trap radiation belts that would kill any known organism. Moons with subsurface oceans that might harbour life in environments completely unlike Earth. Understanding this diversity, understanding how different planets can be, is essential for understanding planets in general, not just in our solar system but around other stars. When we find an exoplanet and try to characterize it, we need to know the range of possible configurations. Jupiter teaches us that range. Jupiter also teaches us about habitability in unexpected places. We used to think habitability meant surface liquid water, a planet in the habitable zone around its star where temperatures allow water to be liquid on the surface, Earth-like conditions. But Europa and possibly Ganymede and Callisto show us that you can have habitable environments in completely different contexts. No surface liquid water, ice shell kilometers thick, but liquid water ocean underneath, kept warm by tidal heating. That's a habitable environment even though it's nothing like Earth. This expands where we should look for life, not just on planets in habitable zones, but on moons of gas giants, on moons of ice giants, in subsurface oceans throughout the solar system and possibly throughout the galaxy. Jupiter's moons might be more common sites for life than Earth-like planets, because there are a lot of gas giants with moons. And if even a fraction of those moons have subsurface oceans, and the physics suggests many of them might, then there could be more habitable environments in oceans than on surfaces. That's a profound shift in thinking, and it came from studying Jupiter's moons. Here's another thing. Jupiter shows us how planetary systems interact, how one massive planet can dominate the dynamics of everything around it, how migration can reshape a system, how moons can affect planets, and planets can affect moons through tidal forces and magnetospheric interactions. Our solar system is not static, it's a dynamic environment where objects interact gravitationally and magnetically and through exchange of material. Jupiter is at the centre of many of these interactions. Understanding Jupiter helps us understand how planetary systems evolve over billions of years. And there's a counterfactual question worth considering. What would the solar system look like without Jupiter? Or with a much smaller Jupiter? Or with Jupiter in a different orbit? The asteroid belt would probably look different. Maybe there'd be a planet there instead of asteroids. Mars might be larger. If Jupiter's migration didn't limit Mars's growth, Mars could have accumulated more material and ended up Earth-sized or larger. The outer solar system would be different. Uranus and Neptune's orbits might be altered. The Kuiper belt might have a different structure. Earth might be different too. More impacts from asteroids, fewer, a different tilt to its axis from different gravitational perturbations. It's hard to say exactly, but Jupiter's presence has shaped the solar system we have. In some planetary systems we've discovered, there's no equivalent to Jupiter. Just small planets, or hot Jupiters that migrated inward and disrupted everything else, or configurations we don't have analogues for. Those systems evolved differently. They had different outcomes. Jupiter is part of why our solar system is the way it is. Understanding Jupiter helps us understand why we're here. Let me bring this back to where I started. Jupiter is not what you think. It's not a simple ball of gas. It's not a gentle giant protecting Earth. It's not fully understood. It's a complex, dynamic, hostile, fascinating world. Layers of hydrogen in exotic states, a magnetic field that extends millions of kilometers, radiation belts that destroy spacecraft, moons with subsurface oceans, atmospheric dynamics we're still trying to model, a heat source we can't fully explain, a history of migration that shaped the solar system. Every time we send a mission to Jupiter, we learn something that surprises us. Volcanism on Io, subsurface oceans on multiple moons, polar cyclones in geometric patterns, lightning at high latitudes, radio emissions we can hear from Earth. The picture of Jupiter that's emerged from decades of exploration is far stranger and more interesting than the simple gas giant description suggests. And there's more to learn, more missions coming, more data to analyse, more discoveries waiting. That's what I want you to take away from this. Not just the specific facts, though those are cool, but the broader point that even a planet we've studied for centuries, that we've sent multiple spacecraft to, that we can see with binoculars from Earth, even that planet is not fully understood. It keeps surprising us. The universe is more complex than we think. Always. Every time we look closer at something, we find details and phenomena and behaviours we didn't anticipate. That's what makes science exciting. Not the facts we already know, but the things we discover when we actually go and look. Jupiter looked like a banded ball of gas through telescopes. We thought we understood it. Then we sent probes and found out it's radiating its own heat. Then we found volcanism on Io. Then we found subsurface oceans. Then we found the polar cyclones. Each discovery changed our understanding, and there's more coming. The next mission might find evidence of life in Europa's ocean, or discover something about Jupiter's interior that requires rewriting the textbooks, or measure something about the magnetosphere that reveals new physics. We don't know what we'll find. That's the point. That's why we keep exploring. Jupiter is not what you think. It's weirder, more hostile, more dynamic, more interesting, and it's not finished surprising us. So the next time you see Jupiter in the night sky, and you can see it with your naked eye, it's the brightest thing after the Moon and Venus. Take a moment to think about what you're actually looking at. Not a simple ball of gas, but a world with atmospheric bands that extend thousands of kilometers deep, with a magnetic field that stretches across the solar system, with moons that might harbour life in oceans beneath ice, with mysteries we're still trying to solve. That bright point of light in the sky is weirder than you think, and that's beautiful.